And I'll hand over to Ajeet.
Great. Okay. Hello. So let me start by, actually, I'll talk for a second. Okay. So last time we went through some reasoning about how to construct the Lorentz transformation. So the idea is we live in this 4-dimensional affine space. So there's 3 dimensions of space and 1 of time. But unfortunately, thinking about the dimensions as space and time isn't a very good way to do it. We were thinking about simultaneity, and we came up with some thought experiments that made that notion kind of vanish. And we were thinking about time, and by experiments or by some Einsteinian reasoning, if you like that part better, we reasoned that time changes based off your reference frame also. So then space and time aren't the best way to set up the bases for the different reference frames. But we argued that this causality grid is a better one because everyone agrees on those lines, on the causality lines, because everyone has to agree on the speed of light or the speed of causality. Okay, and then from that, we argued about Lorentz transformation. Now, I wanted to start off this lesson by clarifying or by making that argument more linear. So the reason that we run into trouble when we try to construct this argument about what the Lorentz transformation should be is that if you try to do it as like a deductive argument, like step 1 implies step 2 implies step 3, then we get into issues about forcing things onto reality. So it's never going to work as a fully deductive argument going from math into space or math into physics, right? So if we say this is the mathematical structure, at some point we're going to say, okay, well, why is that the physical structure? Okay, well, it's not literally, it's just a model. Okay, so this is kind of why I put that that little section about the Ouroboros at the beginning of lesson 1 in the notes. So really what we're doing is we're constructing a mathematical model that works for some observations. What are those observations? Well, we've noticed that the speed of light is constant every reference frame, and we've noticed that time slows down for certain observers. We could start with a measurement of how much time slows down and argue from there, but instead, I want to walk you through an argument of why the transformation should be what it is. So, okay, let's get to it. So I put in the chat a link to my website, so that has the updated notes. Obviously, this is still a work in progress, so there's still a couple gaps, but okay. So this should be those updated notes. Hold on. That's not right. Hold on. Okay, I may have lied to you that those are the updated notes. Okay, I will update those notes at the end of this lecture because that takes a second to put it on the site. Okay, so let's take a look at this. Okay. All right, so here is our inductive argument about the causality boost. So inductive argument, so one step implies or suggests the next one, but doesn't nail it down exactly. So at the end of this, once we have the Lorentz transformation that takes you from one reference frame to another, you can justify that by saying, you know, that does indeed match our observations. So that can give you confidence in it. Right, but I wanted to try to motivate it in, you know, a little more physical way along the way, as opposed to just saying, oh, well, it works compared to experiments. Okay, so like we started at the very beginning, we have affine space. We have affine space, and we'll start in 1-1 space, so 1 dimension of space and 1 of time, so just 2-dimensional affine space. Space and time are the intuitive ways to construct a basis. So here's a basis B. We have x hat and t hat for some space dimension, some time dimension. And then we have some other reference frame that has another space coordinate, another time coordinate. And the idea is we need to figure out how to transform our space and time coordinate into their space and time coordinate so that we agree on everything. Okay, so the other reference frame is moving with the relative velocity nu to the first. Great. Now, so we want some linear transformation that takes us from this basis B to this other basis B prime. Okay, and so this is the notation we're going to use, and I can go over this notation. Actually, let me slide up to Proto-Einstein notation. Okay, Proto-Einstein notation. Okay, so why do I call it Proto-Einstein notation? So I saw this in a linear algebra textbook in college, and I really liked it. And it turned out to be the way that these coordinates work, or these indices work, is similar to how tensor algebra works. So it's a good precursor to more general stuff in multilinear algebra. Okay, so then a vector is just denoted by a letter. And then in brackets with a little subscript, the subscript is the basis of that vector. And if you put an equal sign after this, you would put a list of coordinates that says how to express that vector in that basis, right? So vectors are these geometric objects that just exist. But when you pick a basis, every vector for each basis, the vector gets a different set of coordinates so that it can be expressed in that basis. So then if you put an equal sign here to some vector of coordinates and an equal sign here to some vector of coordinates, those coordinates are going to be different. So different column vectors. I'm using the word vector in two different ways, right? Like, I guess on the left-hand side, I'm using vector as literally as in the geometric object. And on the right, when I'm saying vector, I mean like a set of coordinates, like a 3-tuple or whatever. Okay. And then here, the change of basis matrices, I haven't decided, so here I just use I, but I'm going to use L later. So the idea is that a change of basis matrix doesn't change. So the idea of a change of basis matrix is you just change the way you look at the same vectors, which ultimately is the viewpoint that I'm trying to take in the seminar, where instead of I'm trying towards the end of the seminar, we're going to move towards language of, instead of saying, okay, the Lorentz boost moves the events in this person's reference frame to the events in this person's reference frame, we're going to say, okay, the Lorentz boost is a representation of a basis change, and that change of basis changes how the two observers measure those two events. So we're all looking at the same stuff, the same vectors, but we get different coordinates based off of the basis we use. And that is, I like this perspective because it helps to demystify the relativistic effects you see, right? So if you have the same vectors, right, but we just measure them differently using different bases, and then that is the source of weird relativistic effects. That is we can see then that those effects are non-physical, right? The ultimate goal here is to show that these weird things like time slowing down and space squishing and simultaneity not being preserved are non-physical things. Just like in linear algebra, differences up to basis change are non-physical. I guess I shouldn't say non-physical in a math context. I guess you know what I mean in a linear algebra context, right? If you can just change the basis to get from one coordinate expression to another, then that's just a viewpoint. Okay, cool. And you can stop me anytime if you have questions. Okay, cool. So
I actually
right.
have, sorry
Yeah,
to interrupt.
I
actually have one question. I thought this was the first lecture, but I now realize that you guys have covered some of the contents. Is there any way I can access the recording of the first lecture?
Yes, actually on a YouTube link, and I can just email you that if you put your email in the chat box.
Okay, thank you so much.
Yeah.
Thank you so much.
Cool. And actually, since we have a small enough audience here, if you tell me what you know about special relativity, I can, because this actually argument here kind of does a summary of the first two lessons. So if I know what you know, then I can help bring you along. So what do you know or not know about special relativity?
I know essentially like nothing of the mathematics behind it. I know like the concept, kind of. I saw it in a class, a physics class last semester, but nothing about the math.
Cool. Okay, that's fine. Right. So great. So I think I can. Right. I guess you should watch the other two lessons for more details, and then the notes, of course. But yeah, I think I can pull you along then. Okay. So right, we have an affine space, which is like a vector space, but there's no origin. And if you pick an origin, then that becomes a vector space. And the origin is an arbitrary choice. So we have two different observers. Let me just scroll up to the first picture real quick. Those are a bunch of examples. You don't need all of those. So we have an affine space, and this is one observer, and this is another observer, and they both have their own origin, and they both have their own basis. We can always just translate the origin over, so we don't really worry about that here. We just say they agree on the origin, and then it comes down to picking basis vectors. Now, we have weird effects that we see in experiments of like time slowing down and stuff when one observer is moving relative to another. So these time and space axes that we see, it's not as simple as just translating them across affine space. They're going to get tilted in some weird way. And we're trying to deduce how that should be. And the two postulates that we're using, the two axioms, as a math people, that we're using to try to get there are Einstein's postulates. Einstein told us that the speed of light in every reference frame is the same. I've been calling it the speed of causality. So the speed of causality in every reference frame is the same, and that physics should be the same in every reference frame. Okay, great. Okay, so right, so we have two different bases in the reference frames. Here's a space one and space and time one. Here's another space and time one. And then here's a linear transformation that takes us from the first basis to the second basis. So B to B prime. And we can just denote that, we can also denote this by L sub nu, because this really just depends on the relative velocity of the two bases. So remember, there's no such thing as universal velocity, there's just relative velocity. Okay, so space, like we talked about last time, is dependent on a notion of simultaneity, which isn't invariant. How can I summarize that really quickly? So it's actually probably a good refresher for the other two participants also. So we have a little experiment where we have like a train and two people standing in a train, and halfway between them, there's like a laser that goes off to zap them both. Within the train, if the two people are equidistant from the laser, they'll get zapped at the same time. Maybe it takes 1 millisecond for the light or 1 nanosecond for the light to get to them. But the problem is, what if you have someone standing on the ground next to the train? Well, they're going to see the two people in the laser moving, but the thing is, the laser light is also still moving at the speed of light. It doesn't add, like the velocity doesn't add. Like if you're in a car and you throw something out the window, the speed of the thing out the window from the perspective of someone on the ground is the speed that you see it going at plus the speed of your car. But speed doesn't add in special relativity. Not the same way anyway, and light always goes the same speed. So you get these weird things where the observer on the ground is going to see one of the two people in the train kind of like running away from the laser and the other person running into the laser. So they're going to see one person get zapped before the other. So this means that inside the train, it looks like the people get zapped at the same time, and outside the train, it looks like the people get zapped one then the other. And if you were in a faster train, you would see the other person get zapped first. So the point is that simultaneity is like this made up concept that we like to believe, but it's non-physical. And that's like it's kind of a deep argument, but okay, so let's leave it at that for now. So space is dependent on a notion of simultaneity, but simultaneity is relative. So that's not really a great starting point. Okay, time by experiment or by some Einsteinian reasoning that we talked about last time is also relative. So that's also not a great place to start. We would like a basis choice that isn't so relative, right? Okay, so space and time basis isn't a good intuitive framework. All right, the causality grid, something we can agree on. Okay, so let me go to the causality. Let's look at a causality grid. So here is a space-time diagram. Space is on the x-axis, time is on the y-axis, and these diagonal lines correspond to light rays. So if you haven't seen a space-time diagram before, something moving with a certain slope here, the inverse of that slope is its velocity, because it'd be time over space, then you flip that to space over time. And the speed of light, or the speed of causality, we're setting to 1, which means the highest slope you could have for an object is 1. So anything that's like a real object has to have a lower slope than that, or a higher slope than that. And then light itself follows along these causality lines. Okay, so everyone agrees on the causality grid because we all have to agree at the speed that light goes. So this linear transformation, at worst, it has to. Oh, here, let me set up a vector space real quick, or a basis for our vector space real quick. So it's how the forward light vectors be 1, 1. My brackets disappeared. Okay, be 1, 1, and my backwards light vectors be -1, 1. So if you just go to 1, 1, that's a diagonal line with slope 1, which corresponds to a light ray moving to the right or moving forward. And 1, -1 is a vector that corresponds to a light ray moving to the left, at maximal speed, at the speed of light. Okay, so we have these two vectors that are linearly independent, and we know, so I mean that already is justification for them to be a basis, but even better, we know that at worst, our linear transformation can only stretch these vectors. They can't rotate them. To rotate them would be to change their slope, which would mean that in the other reference frame, light moves at a different speed. Okay, so because slope is the inverse of the velocity on our little diagram, so we can't rotate them. So then all that's left to do in a 2x2 linear transformation is to stretch them. But what are vectors that can only be stretched? Those are eigenvectors. So we have two linearly independent eigenvectors. Fantastic. That's the Eigen Basis. It's the best basis you can use. So the Eigen Basis is just F and B. Cool. And then just tautologically, the linear transformation in the basis of maybe I should put a C here and here. I don't know. I need to hammer out exactly how to use this notation, because sometimes I'm using this as a change of basis matrix. I guess I'm always using it as a change of basis matrix. Maybe I should put C and C prime here. That's a good way to do it. Yeah. Okay. So the linear transformation from C to C prime. So my forwards and backwards vectors to your forwards and backwards vectors. Well, a linear transformation in the basis, or in terms of the basis, in terms of the Eigen basis, has to be diagonal, and that's just a linear algebra statement, right? It's just tautological, right? A linear transformation with respect to the Eigen basis has to be diagonal. All you're doing is stretching. Okay, great. So we've reasoned ourselves into a nice basis where our linear transformation has to be diagonal. So now we have to find A and B, which also means we just have to figure out what the eigenvalues are. Oh, we have a chat. Okay, cool. Okay, so now we just have to figure out what the eigenvalues are. Okay, well, what's another interpretation of these eigenvalues? Something like maybe more physical. We talked about last time how photons don't experience time. So that's a physics thing. That's an Einstein reasoning thing that you might or might not feel comfortable with yet. But I'm going to insist on it for this argument that light doesn't experience time. Okay, so photons don't age. They're timeless. They just go on forever. I mean, what does go on forever? What does that even mean? The photon's not keeping track of time. It just hurls through space and time, and it's just this one line. And time slows down as you go faster and faster. And the way that works when you go at infinite speed is time collapses down to a point. The photon's entire life happens in one instant, past, present, and future. Okay, so that's the life of a photon. So then when we draw these diagonal lines and we parameterize them, we have to say, oh, well, this is the span of like the forward vector, the span of 1, 1 over all of R, so that we can span this vector in a linear algebra sense into like this line to get one of the lines in the causality grid. We have to span this vector, right? But like, what does that mean to span that vector? How do we pick a parameter to parameterize that line? So parameterizing a world line, which is just the path that like a normal thing like a human or a baseball takes through space and time, you parameterize that by how it experiences time, by its own personal clock. You give it a parameter, a parametric curve, like maybe parameterized by a variable s, and s is any line. If I give you a line, there's an infinite number of ways you can parameterize it, and if you want the speed along the curve to be a certain thing, that's a way to figure out which parameterization you want to use. But let's just say I give you a line and then I say parameterize it. You have a freedom there. Okay, if it's a world line, then you want that parameterization to be consistent with the way that object experiences time. That makes sense. Okay, but how do you pick up parameterization for this line for something that doesn't experience time? Well, the answer is that there's no like good way to do it. You have freedom to choose. How do we parameterize this line, right? So what should the eigenvalues be? Well, that is actually going to be a freedom of ours. To stretch the world line of a photon is like totally fine, right? If you stretch the world line of a normal object, then you get some weird effect where you slow down you're slowing down the personal clock of that object. But if you stretch the world line of a photon, that's an entirely non-physical thing to do. It's fine. It's not even part of the model. The parameterization along the causality grid is not part of the model. It's just a causality grid. It's just a grid, and you have some lines. But parameterization along those lines is totally a freedom of ours. If a photon lives in an instance and then you multiply its entire life by 2, or you divide its entire lifespan by 2, it doesn't care. So, right, okay. So just to recap, your world line is a human flying through space-time. If I parameterize your world line differently, then your personal clock would slow down and everything would be weird. But if I reparameterize a photon's world line, it doesn't care because its whole life exists in an instant anyway. Okay, so hopefully that if that argument didn't make sense, then go ahead and stop me. But okay, so that's why I'm going to insist that we get to pick the eigenvalues. Okay, if you didn't like that argument though, that's fine, because you can just do the math or follow the math and say, oh, hey, we have to figure out what these two diagonal values are. Okay, cool. So right, whether you want to think of it as picking a parameter for the causality grid or picking these two diagonal elements, the eigenvalues, we have some choices to make. Okay, all right. So the first thing that I want to do, I want to look deeper into Einstein's postulate that says that causality or light flows at the same speed for all observers. What does that even mean, right? So a photon's world line is, a line, a diagonal line on our space-time graph, and it moves at the same speed for all observers. How does it move at a certain speed relative to us? Sure, but relative to itself, its whole life exists in an instant. It doesn't care. There's no notion of that. Really, if you look at the math, what Einstein's saying here is that you pick a parameterization of the photon's world, the photon's S apostrophe, so plural possessive, of the photon's world lines. You pick a parameterization of the photon's world lines such that an individual photon, or if you want like an evenly spaced signal of photons, like bip, 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 travels along that world line relative to you at the same speed. Okay. So if you're relative to you, if you consider yourself stationary, if you send out a pulse of light and it flies off a meter in each direction and then bounces off some mirrors that you set up ahead of time and then bounces back to you, then you should be able to calculate how far away those mirrors are by measuring how long the light has been traveling. That's an alternate formulation in and of itself. If you had a whole bunch of mirrors set up everywhere and you send out light signals, maybe use Morse code in light or something to send out signals, and they bounce off the mirrors and they come back to you, and you calculate how long it took to get to you, you should be able to reverse engineer how far away the mirrors are. Saying the speed of light is constant is really just saying there's this fixed relationship between how much time light travels and how much space light travels. Okay, so light. So it's always weird to say traveling through space-time, because when I say the word traveling, you usually think of traveling through space with respect to time. But if you say traveling through space-time, the only way it makes sense is to say I'm changing like a delta space and a delta time with respect to my local clock, my parameterization, the parameterization of my world line, how I'm perceiving things happening, okay, my age or whatever you want, or my stopwatch, whatever. But that sentence breaks down for photons. Like the photon's moving at a certain speed through space-time, a certain direction through space-time. The photon, okay, so here's a sentence for you that doesn't make sense anymore. The photon moves with slope 1 through space-time with respect to what? With respect to its personal clock, but doesn't have a personal clock. So it moves at speed 1 through space-time with respect to what? It breaks down. It doesn't make any sense anymore. If we dig deeper, really what Einstein means by this is that you pick a parameterization of the causality lines, the causality grid, such that the speed of light for a certain signal or whatever is always 1 or c or whatever. Okay, so using this reasoning, let's think about what we should have to do to the causality grid to make it so that the other observer, the moving observer, is doing something sensible to us. So at first glance, if we set up the parameterization of the causality grid our way, and then we look at a moving observer, they're chasing causality, right? They're chasing these light waves. The light waves that are moving away from us, they're chasing the light waves moving in the same direction they are, they're chasing them. And the light waves moving in the opposite direction, they're running away from them. So if that's actually how everything worked, if that's the same parameterization of the causality grid for them as it is for us, then they would perceive the light that they're chasing to be moving slower than 1 or than C, and the light that they're running away from to be moving faster than C. If it's like a Doppler effect. Like you have ripples of sound that are just emanating through air all over the place, and if you move close to the speed of sound, you're chasing those sound waves in one direction and running away from them in the other direction. Like a car coming towards you and a car going away has a different pitch, because in one direction it's like collapsing up these sound waves, in the other direction it's like running away from those sound waves. And if you go faster than the speed of sound, you get a sonic boom when you catch up to those sound waves themselves. There's no light booms because you can't go fast, you can't break the speed of light. So anyway, so what were we saying? Right. Okay. So we don't want like this light Doppler effect doesn't this causality Doppler effect doesn't work in this way. You can't catch up to light waves the same way you can catch up to sound waves. It is that's a postulate of Einstein's relativity. So what are we going to do? We're going to reparameterize this causality grid, because that's a freedom of ours anyway, such to account for the motion of the other observer. So what we're going to do is we're going to stretch the causality grid in the direction they're moving by 1 plus nu, and stretch it by 1 minus nu, which will be some number less than 1, along the other direction. So F's eigenvalue is going to be 1 plus nu, and B's eigenvalue is going to be 1 minus nu. I remember nu is something between 0 and 1, so 1 minus nu is just some positive number. Okay, cool. So we squished the causality grid in one direction and stretched it in the other direction to account for the other observer seeing the speed of light the way they're supposed to. Okay, great. We have one more issue to handle, though, is what's the determinant of that matrix? If A is 1 plus nu and B is 1 minus nu, then the determinant of that matrix is 1 minus nu squared. Dang, we seem to have squished space and time in the process of doing this transformation. If nu is 0.5, then 1 minus nu squared is 0.75, which means that the whole volume of space-time changed, it gets squished down by a factor of 0.75. This violates Einstein's second postulate of special relativity. Why? He said that physics is the same in all reference frames. So if you start saying that at first you might be able to say, oh, well, maybe it's not so bad if I consider the universe to have this kind of scale and that moving observer considers the universe to have like a squished scale, right? Like it's similar, like it's a similar object geometrically, but it's smaller. Why is that so bad? Well, the reason that's bad is that lattices and chemicals and chemical processes and nuclear processes have properties based off of these distances. If you just start squishing objects, they have different chemical properties, and physics isn't going to work the same. So maybe that's a long way of saying you want reality to have the same scale in the other reference frame. Okay, we want this linear transformation to have unit determinant. Maybe that's something we should have said at the beginning. It seems reasonable enough that we don't want to stretch all of space and time. Maybe we stretch space in one direction and space time in the other direction, and stretch time in the other direction. But the total volume of space time, we want that to be the same. Okay, that's the argument. So we multiply the whole matrix by this factor to make sure that the determinant of the whole matrix is 1. So then this is our Lorentz transformation between the causality bases. It's pretty simple. It's diagonal, and then you get, this is called the Lorentz factor, 1 over square root of 1 minus nu squared. Okay, so right, this Lorentz factor pops up all the time in observations. It's the factor that time gets slowed down by at a certain velocity, that space gets squished by in a certain velocity. Okay, and we're going to see that in a second, actually. But okay, so here's our Lorentz transformation in the causality basis. Okay, now let's move back to the space and time basis. Okay, I'll type this out later. The exact transformation. It's super simple. Just going from the 1 0 0 1 basis to the 1 1 1 negative 1 basis. I'm sure You probably actually literally did that calculation at some point in a linear algebra class. But anyway, this is what the Lorentz transformation looks like in the space and time basis. So from B to B prime. It looks it looks pretty similar actually, but it's a little different here. It's not diagonal anymore because we're not using the Eigen Basis. And this is what physicists will give to you. Physicists will start off a class saying, this is Lorentz boost. This is how you change space and time between reference frames. And then from their perspective, you have space flowing into time and time flowing into space. It's not a diagonal matrix. If it was a diagonal matrix, space would stay space and time would stay time. But as we see, when we go into the spaces of B and B prime, though space and time evidently weren't the eigenvectors. It's not a diagonal matrix in this basis. Right, yeah. So intuitively, we want to think that, you know, space has to stay space and time has to stay time. So then those should be the eigenvectors. You stretch along space and you stretch along time in some way. That's not how it works, apparently. So if you insist on thinking about this is space and this is time, then you're going to get weird things like space gets rotated into time and time gets rotated into space. Rotated might not be the best word. Sheared maybe is a better word in a linear algebra sense. But anyway, so space gets sheared into time and time gets sheared into space. Right, so that's super ugly. That means that, you know, I prefer to take the perspective that that means our definitions of space and time weren't too good to begin with. You know, saying it like this kind of implies that space and time are these grand immutable things. It's like, sure, yes, you can think of space and time if you want to, but the space and time aren't like the grand universal space and the grandfather time ticking away that you thought they were. They're these, there's just these like arbitrary components that you defined in space time that actually shear into each other in other people's reference frames. Okay, so I prefer to use a different language. Let's talk about the thing that's invariant, that everyone agrees upon. Let's talk about, you know, the eigenvectors. Let's talk about the forward causality lines and the backward causality lines. The lines corresponding to light waves moving to your right and light waves moving to your left. Or if you want, like light waves moving forward, and you could pick a different causality basis that's light waves moving forward to the right and light waves moving backwards in time to the right if you wanted. This was a choice. I'll put a section on that later. That's just a choice. Okay. Great. So right. Okay. Yeah. So the physicists will try to sell you on this Lorentz boost, but I want to use this Lorentz boost. Okay. Cool. So yeah, that was a recap of last time, and also like a more precise argument about where this thing came from. I used kappa for it here, but I think I'm gonna go back to L. Yeah. Okay. So any questions on that? The next thing I want to do is go into Mathematica and show you guys something to do or how to model this actually. Okay, cool. Thanks for coming, Rodrigo. Yeah. Okay. Off to Mathematica. So I said last time I was going to post the Mathematica notebook, and I did not because it's not finished. And it's I want to give you something that works. So also part of what I want to do in the seminar anyway is teach you Mathematica. So I figured we could do it together here, or do part of it together here. So you can follow along if you want, or you can just watch me do it. But I'm going to show you how to make something. So what I want to show you is I want to show you what actually is invariant. There's this really cute concept called causal diamonds. It's not in like any physics textbooks that I've seen. It's just like some PDF that someone made somewhere about a way to think about this stuff, and I really love it. So that's the perspective we're going to take. So what we're going to do is I'm going to show you in Mathematica how to like do a linear transformation on well, really, I guess I'm going to show you how to model a general linear transformation on some points. And then we're going to use specifically our linear transformation. And then I'm going to show you how to see these causal diamonds. And then ultimately that will motivate something called the space-time interval, which I mentioned a little bit last time. The space-time interval is a value that is consistent between reference frames. So what Newton thought is that the Euclidean distance between 2 points is invariant between reference frames. That doesn't change. Space is immutable, time is immutable. The Euclidean distance through space and time, in fact, is fine, but that's not the case. The Euclidean distance between 2 points in space-time in general will change under a linear transformation, under a Lorentz transformation. But there is something that won't change, and it's called the space-time interval. Okay, so Euclidean distance is, you know, x squared plus t squared, or x squared plus y squared, right? And that is related to a quadratic form in linear algebra. So similarly, our space-time interval, which I'll just spill the beans, it's x squared minus t squared. That also corresponds to a quadratic form in linear algebra. And just like the Euclidean norm preserves circles, right? There's like this deep connection between the equation for a circle and Pythagorean theorem. Just, you know, it's the same equation. There's a similar thing for, well, a very, very, I mean, analogous, I should say, thing for the space-time interval. X squared minus t squared is the equation of a hyperbola. So instead of a circle being invariant, a hyperbola will be invariant, and that's what we're going to try to show. Okay, cool. So let's do this. So I'm going to use a manipulate block to start. Actually, let's start simpler. So let's just make a plot. So I'm not going to plot anything on it. I'm going to do x from -2 to 2 and t from -2 to 2. Plot range 2, aspect ratio 1, image size medium. And you can stop me anytime if you have Mathematica questions, or other questions, of course. Oops. Oh, let me. Right, and plot just takes the one argument here. It doesn't care what we call. It doesn't care what we call the dependent variable. Okay, so here's our plot. That's just plot, and I'm not plotting anything right now. Okay. So now let's do show, and I'm going to put on here. So show just takes two things that are the same size, like plot and graphics are both two-dimensional like objects, and it overlays them. So graphics gets a list of things. So just to show you what's going on, let me put a point in here. So I'm going to put a point, and the point's going to be x comma t. Whoops, I didn't define x and t. So 1, 2. Great, that's too high. 1, 1.5. There's a point. Cool. And you know what? Actually, in the plot, I will go ahead and plot something. I'll plot the functions x and -x because that gives us a nice causality cone. Great. Oh, and this is an opportunity to show you something else in plot. I'm going to call plot style. You can pick the color. So I'm going to pick. You can also pick whether it's like a dash line or whatever. I'm going to put yellow for both. Ah, that sucks. Let's put green. Yellow just doesn't show up very well, so we'll put green. So our causality grid is green. Our causality cone is green. Okay, so a point here, and let's make that point blue. Blue, and so graphics just takes like this list of commands. It's as simple as you could possibly imagine. It just takes a list of commands, and then it does what you want. So and then it executes those commands in order. Okay, so they try to make it simple. Okay, so we have 1 point. All right, now let me show you the manipulate function. So I talked about this in a previous lesson, but I'll say it again. So manipulate, you can put it around absolutely anything, and then you give it some arguments here that you can alter, and then it gives you sliders or sometimes locators that let you change those values. So let me do this. Let me. So you can check the notes on my website, the Mathematica notes, if you want to see a whole bunch of examples to manipulate, or you can just look up the Wolfram documentation for manipulate, because the documentation for Mathematica is very, very good. So let's initialize this point at 0, and let's actually I don't even need to give it a range. Let's just say locator. Okay, and then our point, we're going to plot it at p. Okay, cool. So now we have a point, and you see a little blue point is attached to my locator right now. It's a little redundant, but okay. So what I want is I want my locator to be a point that I choose, and then I want another point to appear that corresponds to the point after the Lorentz transformation. So what I'm going to do is I'm going to first add a little slider here for the Lorentz transformation. So new, start at 0, goes from -1 to 1. So slider doesn't do anything yet, but it controls some variable new. Okay. Now let's code the Lorentz transformation. So I'm going to do Lorentz, and Lorentz takes in a point x comma t, and then what it does is, I guess I should tell you how I'm doing this. control comma and control enter lets you expand horizontally and vertically to make like matrices respectively. Okay, and then just this dot operation in Mathematica will do matrix multiplication. Great, by default. Okay, so what is our transformation? It's 1 over, so it's also has taken new, and I should probably use the right notation for a function. So Lorentz transformation takes in a vector and the Lorentz and the speed, right, and the relative velocity, and then it does this: the Lorentz factor times 1. Wait. Oh, check the notes on. Always mix this up. Okay. 1, negative new, negative new, and 1. Okay. And then just something annoying is this will give a matrix, even though it's just a vector. So Mathematica doesn't know that we just want it to be a vector. So you have to just put a 1 here just to grab the first element. That's just something annoying. Let's just check that this works. So Lorentz, if you do Lorentz of 1, 0, so what happens to, let's do 0, 1 actually. What happens to like a vector that's just in the time direction, like a time vector with when it's boosted? Whoops, okay, that's not what we wanted. Okay, so instead we're gonna use flatten. What's flatten? So flatten is an operation for lists. What it does is if you have like a list of lists, it I guess it just unions them all together is a way of thinking about it. Yeah. So flatten. So here we see it's expressing it as a matrix. There, now it's a vector. Cool. So that's where 0, 1 goes under a Lorentz boost of 0.5. Interesting. Okay. Well, let's actually put it into the model. So what if my point is instead at exactly p? My point is at Lorentz of p with respect to our variable nu that we already made a slider for. So here's a point. And then as I do a Lorentz boost, we see at that point is going to travel to some other place. So there, that's actually all there is to it. That's the whole thing. That's how to do linear transformations in Mathematica. It's not that bad. Because Mathematica has built-in like matrix operations and stuff, you can type it in exactly as it looks like. So here's a point that you specify however you want. You just can just move it around, and then you specify the Lorentz boost, and then it slides the blue point accordingly. Great. Okay. Right. So now what if we want multiple points? So what I'm going to do is we're going to use something called the map function. So the map function does is it maps a function over a list of things. So P is actually going to be a list of points now. And what we're going to do is map this over it. So points, Lorentz hash new. So this is a pure function that I talked about last time, or implicit function, as I like to call it. So this is a whole function right here. This function, it takes in the argument of hash, it sticks it into V, and then, it takes an argument of hash, it sticks it into Lorentz of this with V as new as the second argument, and then all that inside of point. And this just says that's the end of the function definition. It even says there, function. Great. Okay. So it'll map this function over P, where P is a list of points. So I just have to change my notation to make this a list of points. And we're going to do something called locator auto create to true, which I think I talked about before. So what happens now? We get the same thing, but now if I command click, I can create multiple points. And now P is a list of points, and our whole Lorentz thingy here maps over the list of points. Now we see how they all move under a Lorentz transformation. Cool. Okay, so now I'm going to make an obnoxious number of points so that I can start showing you what this Lorentz transformation does. So it's have some points along a time axis, to have some points along the space axis. Actually, let's just start with that. So, all right, So prepare yourselves. I'm about to demystify all of the things that physicists get hung up on in special relativity. So there's a little bit of an overstatement. We're going to go into more detail. So next lesson will be the really fun one where we start getting into paradoxes. I'm going to tell you all these paradoxes that happen. So they're not really paradoxes, obviously, because like they work, but it's non-intuitive things like just weird non-intuitive things that happen, and then trying to explain them. Yeah, and our explanations will go faster than the way the physicists explain them. Anyway, so right, so two things that we're going to demystify here: time dilation and length contraction. So physicists like to say that when something's going fast, time slows down for it, and they also like to say when something goes fast, space gets contracted for it. Okay, so here's a whole bunch of points along a time axis and a whole bunch of points along a space axis. When we do this linear transformation, we see that the points along the time axis get spaced out farther than they were, farther apart than they were before. So if these are ticks on a clock, and then we boosted this observer that's following this world line to this world line, this diagonal one here, inside the light cone, we see that the tick marks, the ticks of the clock, got spaced out more. So that's what they mean by time slows down for them. So here's our observer at 1 second by their clock, 2 seconds by their clock, 3 seconds by their clock, 4, 5, 6, 7, right? And then for this, when you see the observer moving, you see 1, 2, 3, 4, 5. They're spaced out more. So from the reference frame of the stationary observer, if we just draw our timelines like horizontally, right, as one does, we see that in 7 time steps for us, they just barely did 5. Maybe the 6th one is like right there. Where's the 6th one? Is it close? It's right. Oh, it's up there somewhere. Yeah. That's what we mean by time slowing down. If you take an evenly ticking clock for an observer, and then you hit that observer with a Lorentz boost, that evenly ticking clock, the ticks got spaced out. They got stretched out farther apart. So that's what we mean by time slows down relative to us. They don't notice a difference. Time ticks the same for them. But from their perspective, like, could you tell if time was slowing slower for you? Or was running slower for you? Like, how would you know, right? Like, you measure everything by your clock, and well, I mean, if your clock slowed down, you would notice that because your brain didn't slow down. Well, what if your brain slowed down too? What if everything slowed down, right? You wouldn't notice. It's not really even saying anything physical, right? It's like what if your life is a movie and it's played at a slower speed? Everything happens the same. It's not a physical thing we're saying, and it's not a physical thing the physicists are saying either. The physicists are saying time slows down for them. That's not a physical thing. Like, what does that even mean, right? Like, do they feel like they're moving in slow motion? No, right? It's just that if you insist on drawing these horizontal timelines on your space-time diagram, then you see that the ticks of the clock for the moving observer are stretched out. And that's all it means. Okay. Also, space contracts. So let's see if we can see that. So I want to put these space points, more evenly distributed along here. Let me put them there's little marks here, so I can put them along those. Okay. So remember, even positing a space axis like this to begin with is weird because it demands like some universal simultaneity. It demands that we can even like talk about the space next to us. But I mean, how did I place these here? I would need a space-time ruler that moves faster than the speed of light. I can't even say this. So remember, this dimension is time. So if I say, oh, this point next to me, 1 meter. So I mean, like, imagine like next to your chair where you're sitting, right? Like 1 meter next to you, say, oh, that point. When you said that point, right? That one, it took you more than a light meter as a measure. So light year is a measure of time, light meter is a measure of distance, right? A light meter is also a measure of distance. That's not what we're going for. 1 meter divided by the speed of light is how long it takes information to get from here to that point you're pointing to. It took you longer than that amount of time to point to that point. So like, this is you saying, oh, that point. This is, so some line with like a slope like this is you saying, oh, that point. You can't identify it faster than the speed of light anyway. So, okay, anyway, so let's say that you can have like this like grid of rulers that just expands through all of space and time, Einstein synchronization, as it were, where Einstein insisted there's like this array of meter sticks and clocks that through all of space and time that we can use as a background, right? That's like the thought experiment. So when we hit this with the Lorentz transformation, we see that space gets, the points get stretched out here in the same way that the time points got stretched out. So why would that mean that space contracts? It's the same reason that we said that time contracts. So the time point, so the ticks of the clock got farther spaced out by our time ticks of the clock. And the, well, no, actually I take it back. This isn't the length contraction property. This is, I don't think physicists even have a way to justify this property. Yeah. Okay. I mean, here's just another reason why simultaneity is dumb. This line of simultaneity got stretched out also. Space got stretched out for them, if that even makes sense, right? Space and time both got stretched out. The length contraction thing is something that has to do with like a solid object, which we'll get to later. Yeah. Okay. So I lied to you, but yeah, this is something that I don't think the physicists often even try to explain. Yeah, this whole simultaneity line thing is nonsense. But you know, if it were something, we'd see that space gets stretched out also. Okay. It turns out that space and time get stretched out in, you know, the same way by the same Lorentz factor, and that's why the whole thing works. You know, oh, that moving observer, time is ticking slower for them, and space is contracted for them. Actually, you know what? I can explain this. It's just a little trippy. I'm gonna have to do it with an analogy. Okay, let's do. I can do this. So you gotta bear with me. Space and time are going to be treated very similarly here. I'm going to explain it with time, and then I'm going to replace the word time with space in my explanation, and that should do it. So here is the ticking of a clock for a stationary observer. Here is what that clock looks like for the moving observer from the stationary perspective. The points are stretched out farther in time. So if we draw these horizontal timelines, we see that space, their points are we've you know less. We've done less time clicks. So from our perspective, their time measuring device is running slow. Okay. All right, let's do it again. So here's space. Here's ticks of space. So let's say this is 1 meter, 1 meter, 1 meter, 1 meter. Maybe there's like a block of lead on the ground, or you know, just use the earth, right? Like rocks have a certain, you know, say there's one type of rock under your feet, and you know the lattice structure of that rock, so you know the spacing of all the atoms in that rock. So you can use a microscope and count how many atoms deep you are, you know, left or right, and then there you have a way of, you know, measuring the ground below you. You have some space rulers, just like a clock is like a time ruler. Okay, so you go to the moving observer's reference frame. Notice we can go either direction, like it doesn't matter which way the observer moves, as long as they have a relative velocity to us. So we go to the reference frame, and it seems like their space clock is running slow also. So just like how a time clock running slow, means that time slowed down for them in physics parlance, a space, so let me say a time ruler. A clock is a time ruler, a ruler for time. Okay, a clock is a ruler for time. Saying that the time ruler is farther spaced out means time slows down for them. We say that, you know, since the space ruler got farther spaced out, space slowed down for them. No, okay, the word we're looking for is contracted. I know it still looks like space is getting stretched out, but that's, maybe you believe me. If time and space are treated the same in this setup. So the time points get the clock ticking slower is space slowing down, and the space ruler getting stretched out is space getting contracted. So from our perspective, this is 10 ticks of space. For them, it's only 6 ticks of space. Their ruler is too big. It's really hard to imagine. Okay, maybe you believe me at this point. Yeah. But anyway, when it'll be more apparent later, because I unlied to you. This does show the same point of space contraction. It's just hard to get the words to sound right. But when physicists talk about space contraction, they're actually talking about something a little bit different. They're talking about an object with some sort of length, and that object gets stretched out in a weird way, and they label something about that space contraction. But it's the same effect going on here. There's a half lied too. Anyway. Okay, cool. Questions on this? How do we feel about about the Lorentz transformation and how it stretches these points out. Okay. All right. So great. So now I want to show you causal diamonds. So this should be fun. All right. So what I'm going to do here is, instead of a map of points here, I'm going to map the Lorentz factor over all of these. And then to that map, I'm going to type the word polygon. What does polygon do? Polygon just makes a polygon out of those points. Simple enough. So there's a polygon. And if we hit it with a Lorentz transformation, the polygon gets distorted. That's pretty cool. I think it's pretty cool. Okay, so there's the new polygon. Let me draw 2 polygons. I'm going to use blue for the original. I'm going to use red for the shifted one. Polygon, map, and then we're just going to do, oh, we don't need to map, just have a P. So the first polygon is just what happens. The first polygon, let me draw a polygon. Stop talking for a second and draw polygons, hold on. Okay, here's a polygon, okay? That's the polygon in our coordinate system. So, I mean, what's a polygon? What's a polygon in space-time? So this is 4 points in space-time that we're keeping track of. Maybe let's see. Actually, I'll just tell you. So an example of what this is if you do a little experiment where you set up 2 mirrors and you send off laser light from you in both directions, and then that bounces off the mirrors and it comes back to you. So here's you, and you send off light in both directions. It follows this causality line because it moves at the speed of light. This event here is bouncing off the left mirror. This event here is bouncing off the right mirror, and then they both come back. And this event is you recording that both of them got to you. You recording that both of them got to you. And if they didn't get to you at the same time, that means that there's a gravitational wave passing through you. So let's just, I'll talk about that later. So let's say they got to you at the same time. So they got to you at the same time because we live in a flat space time for this experiment. And then that means that you should be able to calculate how far away the mirrors are because you know the speed of light. You know how long it took and you know how fast light goes. So you can calculate how far away the mirrors are. Great. That whole experiment takes place inside this little causal diamond. If you want your experiment to work, you have to control everything inside your causal diamonds. If there's other things going on, like there's dust in the air inside of your little causal diamond. So what I mean by that is if there's dust in the air in the space between you and the mirror during the time that the light is traveling, you're going to have issues. Okay, I guess strictly you just have to control it along these lines, but that's kind of weird. Okay, so this causal diamond is the area of your experiment, the distance between. So it's not just the physical space area. It's not the physical space area between you and the mirrors, right? That would be like some horizontal looking thing here that you would need some impossible space-time ruler to even talk about. It's the space-time. It's like a space-time area is a space-time area is how we should think about area. When you think about like a plot of land, a plot of land is very static, right? Let me give you an example. If I want to talk about the moon rotating around the Earth, right? I'm flying above the solar system and I want to talk about the moon rotating around the Earth. It takes 28 days. So I want to follow the moon's path around the Earth. If I'm floating above the solar system, the Earth is going to be moving around the sun and the moon around that. So then the moon is actually going to take like this kind of spirally thing, part way around the sun. It's like this weird, like polar curve. Like just if you in high school when they showed you polar curves, they showed you limicons and roses and stuff like that. It's just some weird polar curve, right? But you don't care about that part. You don't care about the part that goes around the sun. You want to zoom in and just attach your reference frame to the Earth-Moon system and then watch the moon go around the Earth. That's how you want to visualize this whole lunar cycle thing. Okay, so this is a weird analogy. I'm like comparing space to time and space to space. But anyway, when you talk about space, really what you're talking about is how that space is going to, if you talk about a location in space, really what you're saying is that location in space when light gets there. So I denote these 2 mirrors, but I don't mean the mirrors, in some simultaneous sense, because that doesn't exist. I mean those mirrors by the time the light gets to them. So the mirrors don't have to strictly, they don't have to in a time sense, right? If we use these messy notions of space and time, okay, using the messy notions of space and time, you don't need the mirrors to actually be at those positions in space at the beginning of your experiment. You just need them to be there by the time the light gets there. Okay, let's do away with space and time and just talk about causality. So, all right, you follow these causality lines, the light bounces and it comes back. There's your causality square, okay? What happens when we translate it by Lorentz boost? Cool, all right, so this, our blue causality square is it for us, and this is the causality square as viewed by an observer moving at velocity nu. So notice it went the opposite direction as nu. That's because this is what it looks like to that observer. So we've overlaid the two reference frames of us and the moving observer. So we see the causality square got stretched out. It turned into this parallelogram. Something that we can ensure from a linear transformation is that this has the same area as the original one. Why? Well, it has the same determinant, right? So if you, how do we see this, right? So how do we see this, right? So the area of, so a little square on a little diamond, a causal diamond on our graph is created by one side length is an f vector, a one, like, this f, the f vector goes 1, 1, and the b vector goes -1, 1. So you have some weights on the f vector and some weights on the b vector, and those two things create this causal diamond. You add those two vectors up. It's a parallelogram. It's it's just like normal vector addition, forming a parallelogram, tip to tail, however you want to think about it. Okay, cool. So we have this vector here, the forward part, and here's the backwards part. And then if you take this vector f, the length of it, and you multiply it by the length of this vector, you get the area of this diamond. So it's a diamond is a rotated square, right? And so here, so it's a rotated rectangle. Let me move a little bit to here. Okay. I need this to be following causality lines. I need more causality lines. Whatever. Okay, so I'll put more causality lines later. So actually, let's do it now. Table. Button. Table k from -5 to 5, k and or kx x plus k and -x plus k. Great, cool. Where'd my causal diamond go? I got rid of it. One. Okay, it didn't reach all the way out. One. There's a causality grid. I made it in a pretty barbaric way with plots. I wouldn't do this. In the other notebook, I make it with graphics with lines. Here I just plotted I plotted 66 lines. Okay, that was a barbaric way to do it, but whatever. Okay. Oops, wrong order. Oh yeah, the polygon feature doesn't care if it's convex or concave. It'll just do it. It'll just connect them in the order that you put them in. I think there's a separate Mathematica function for concave polygon if you wanted to automatically figure out what the concave polygon with the points you gave it is. Small theorem for you. If you have a list of points, there's one unique ordering of them, or I guess two going the opposite direction, that correspond to a convex polygon. If you permute any of those points, you're going to get a self-intersecting thing. Pretty sure that's a theorem. Yeah, that seems to make sense. Yeah. All right. Anyway, okay. So here's our causal diamond, and we stretch it. And okay, here's the cool part. We can count the area of this thing using the background causality grid. So our blue one here is 1, 2. Let me measure it here before the red one's in the way. Okay. So we have 1, 2, 3. One more thing I'm going to do. Hold on. I'm going to. So the way show works is it superimposes them in the order that you put them in. So if I just put graphics first, then it'll put graphics on top. I'm gonna put all these options into graphics. Okay, so now the causality grid should be on top of our graph. Yay, great. Okay, wow. All right, there. The area of that is 3, or sorry, 9. 9 causal diamonds. So let's stretch it. Oh wait, 9 doesn't have any other divisors. Let me use something that does. What is that? 15. Same problem. Hold on. Can I get a 12 or a 24 or something? Here, 12. Great. 12 diamonds. Okay. Now let's stretch. Ta-da! Also 12 diamonds. Okay, so cool. The eigenvalue, how do I say this the right way? This vector times this vector, they're both eigenvectors, and then we hit them with the Lorentz transformation, which scales them. But we made sure that our Lorentz transformation has a unit determinant. So then the little square that is spanned by these vectors, or the little parallelogram spanned by these vectors, has to maintain its area. That's just a linear algebra thing. There's a couple ways to argue that. Okay, so right, so the area has stayed the same. And with our background of causality squares, we see that it stays the same. And that's great because that keeps all of our physical properties the same. Does that look like 12 to you? 10, and then how 10, there's a little extra going on. Oh, there's 12. Great. Okay. What we're gonna, okay, you'll see that this peaks out a little bit there. That is not an error. That is not a function of Mathematica approximating. This is something that we have to talk about. We will talk about this little extra triangle. Okay. We'll get there. So yeah, but 12 to 12. So this is the causal diamonds approach. The area, the space-time area stays the same. Cool. So like the total energy, so okay, I feel like physics isn't set up super well, honestly. So energy is defined in terms of space and time, right? But space and time are fake. Everything's determined defined in terms of space and time, but space and time are fake. So conservation of energy. So okay, here's the thing. Since you are math grad students, you can handle heavy math. So there's something called Noether's theorem that you might have heard of. It says that any continuous symmetry has a corresponding conservation law in physics and vice versa. And what this is trying to say is that in a super mathy sense is that if you have a Lagrangian, so some function of like position and velocity and stuff like that, or just some function of a function and its derivatives, that's conserved in a system, then you'll get lines along which everything is the same. And it's kind of like a circular statement. That's how all math theorems are, right? Is once you understand the math theorem, you're not saying anything anymore. Okay, so okay, so the physics application is conserved quantities have continuous symmetries. So conservation of momentum is a function of space being symmetric. You can translate everything around, and momentum is conserved. I mean, it's hard to see. You have to think about it for a while, but that's where conservation of momentum comes from, is that space is translationally symmetric. Okay, conservation of angular momentum comes from space being rotationally symmetric. You can take 3 space and go like this, and it's the same. Okay, conservation of energy comes from symmetry through time. So if a system is the same at each time step, then energy is conserved. But this all sucks, right? Continuous symmetries of space and time, because space and time are fake. Let's get something else. Okay, let's do a continuous symmetry along of the causality grid. That's another symmetry, and the corresponding conserved quantity is space-time diamond area. That's the conserved quantity. So if we're doing away with space and time, we have to do away with conservation laws from space and time reasoning, like conservation of momentum and conservation of energy. Next time, we're also going to talk about relativistic kinematics, which is a headache, but we have to do it. So velocity is, so just like space and time is replaced by this like space-time vector of like space coordinates and time coordinates, or even better, causality grid coordinates. Velocity is and energy are replaced by a 4 vector. It's called the 4 velocity, or for us, a 2 velocity, where one component is essentially momentum and one component is essentially energy. And momentum and energy blur into each other the same way that time and space blur into each other, which is a whole headache of its own. But we'll get to that next week or 2 weeks from now. Okay.
So can you talk again about how to interpret this picture? Is there any kind of physical meaning we care about behind the area of the squares, or you said something before about we can imagine if you're at the center point at the present, and you fire a beam of light to the left and to the right, and it bounces off two mirrors and heads back.
Yeah.
Can you interpret now what's the difference between the blue version of that and the red version of that in this picture?
Sure. So, yeah, right. So, well, one way to do, okay, I could avoid your question entirely by saying this is the invariant quantity in special relativity. This is the thing that's invariant. So maybe instead of saying this in terms of something else, we should say everything's in terms of this. This is what's invariant. This is the conservation law. So everything we should talk about causal diamonds. That's the fundamental unit. So away with meters, away with seconds, space-time units.
Except but, I don't care about.
Yeah, you don't care
about causal diamonds.
Cool, that's fine. So so let me explain it like this, right? So then right, so I can give you an answer. So let me draw our diamond like this instead. This thing also preserves its area. Of course, though, if you want to see that in a mathy sense, you can construct any rectangle out of infinitely many little diamonds if you want. So okay, so this thing got horribly stretched out, but its area is also preserved. Harder to see on our turn thing, but if you don't believe me, we can count, but its area is still preserved. Okay, so its area is still preserved. Yeah, that's an easy argument. You can see it can be made out of little diamonds. Okay, so its area is still preserved. So what does this correspond to? This corresponds to an object existing for a certain amount of time. So if I say this object exists and it has a length of 1 meter, so like a bar of lead and it has a length of 1 meter, okay? That statement doesn't mean anything in special, it doesn't mean nothing, but it doesn't mean anything in special relativity. An observer moving at a different velocity is going to see space like squished, and they're not going to agree that your bar of lead is 1 meter, okay? And then if I say this bar of lead is sitting on this table for 1 minute, that also isn't invariant because a different observer is going to say, oh no, the bar of lead was only there for 30 seconds or whatever. Okay, and that's because space and time aren't these independent things. You have to talk about space and time together. So let's have a new statement. Let's say the bar of lead is 1 meter long and it sits on this table for 1 minute. Okay, so the total amount of lead existing in space, so meter seconds, lead meter seconds is our new unit. So there's 1 lead meter seconds, sorry, 1 lead meter minute of things going on. There's 1 meter of lead on the table for 1 minute. Now, a moving observer won't agree for how long it's on the table anymore, and they won't agree for how long it is. But what they will agree on is your light meter minute unit. So the same, okay, right. So the same amount of stuff at every time slice, so conservation of energy or conservation of mass, like, oh, this stuff exists, we do away with that. And also something moving through time at the same speed, we have to do away with that as well. But something that we don't do away with is, you can think of it as just like total stuff. So I mean, I'm making up a word, right? So
so like
let me
the bar of lead, if I see it on the table, it's 3 meters long and it's on the table for 4 seconds, which is a big table. Yeah. And then my friend Bob says, no, it's only 2 meters long and it was on the table for 6 seconds.
Yeah, yep, yeah, that's the idea. It's a little stranger than that even, actually, because you see here, it turns into this diagonal element. So if you take horizontal time slices here, the lead bar would like pop into existence here, and then you know, gradually come into existence, and then hang out here at a shorter length for a while, and then fade out of existence. But this fading into and out of existence is demystified by our space-time ruler things. Everything has to fade into existence because you have to measure it. Like, how do you know it's there? You have to measure it, but it takes time to measure. All you can really say is the left end of it was here when I started my measurement, and the right end is here when I finished my measurement. So it like fades into existence. So this horizontal distance, that's the length contraction that physicists are talking about. Like, oh, look, it got squished. No, it didn't get squished. It didn't get squished. It got stretched through space and time. So to motivate why causal diamonds should be preserved is that you want the same amount of stuff to exist in space and time. So it's kind of weird that stuff can escape from one time into another time, and right. So then at this time slice, it looks like there's not enough lead. And here there's more lead. What happened to conservation of mass? You created lead. And at this time slice, there's less. There's only this little fraction of it. You destroyed lead. So conservation of mass doesn't work anymore. But what does work is total lead stuff in space and time, right? So like it's not simple enough to say conservation of lead. You have to say, I mean, well, maybe that is the right way to say it. Conservation of total lead through space and time. So the lead, so I mean, that's just the thing. Conservation of mass isn't a thing anymore. It's a more general conservation law. The mass can escape into a future time. Yeah, does that make sense?
Yeah, that totally does, actually. Thank you.
Great, cool, fantastic. Okay, great. Okay, now let me do one more thing, and then we'll wrap up for today. So I'm going to do another plot. I'm going to put another plot on here, and that plot is going to be hyperbolas. So I'm going to do, let me put it over here. Okay, oh, right, so yeah, okay, so then in space and time coordinates, our causality basis takes the form of the f vector is x plus t, and the b vector is x minus t, right? Yes, yeah, right, 1, 1, and 1, negative 1. So so sorry, I shouldn't say x plus t and x minus t. What am I talking about? It's, no, yeah, that's fine, yes. Yeah, so x and t are vectors. So then this vector here is x plus t. Yeah, and this vector here is x minus t. Yeah, no, sorry, negative x plus t, right? This one's negative x plus t, this one's x plus t. And if you multiply those together to get the area, you get negative x squared plus t squared. So t squared minus x squared. Okay, t squared minus x squared. If t squared minus x squared is conserved, so is x squared minus t squared. So you could use either. Another way of seeing that is that we could have chosen a causality basis by using this vector and this vector. You just need any two vectors on the causality like cone that aren't parallel. Okay, all right. Now, right. So yeah, okay. So the conserved if the space-time if the causal diamond area is preserved, that means that t squared minus x squared is preserved, or x squared minus t squared is preserved. Cool. So that is in fact the space-time interval. That's our conserved quantity. So what I'm going to do now is okay. So let's do another thing. So if we if the Pythagorean theorem was conserved, if we had the normal Euclidean norm, and distances were preserved, like distances in space and time. So Newton believed that there's universal space, so everyone agrees on the length of things, and there's universal time, so everyone agrees on the clicking of time, which means you also all agree on the Pythagorean theorem in space and time. Like any diagonal line through space and time, you agree on its length because you agree on the x coordinate and the time coordinate, so you agree on the diagonal. Cool. So Newton's actually saying more than just we agree on the Euclidean distance through space and time of 2 points. He said that we agree on the space between 2 points and the time between 2 points. That's just not how it works. But anyway, it works close to that at slow speeds. Right. Anyway, right. So if it was just Euclidean distance that was preserved, Euclidean distance through space and time, then x squared plus t squared is preserved. And that means that the level sets of that are circles. Okay, let me just give an entirely different example. I'm going to do space versus space instead of space versus time. Okay, so when you rotate space, nothing breaks, everything's fine. If you take a book and it has a certain page length and you rotate it, then it has the same page length when you measure along that line. So distance is invariant of rotations. Distance is, yeah, the Euclidean distance in three-dimensional space is invariant of rotations. So then if I say x squared plus y squared plus z squared, you take the square root of that if you want, whatever, to get the distance between 2 points, and then I rotate everything, the distance is preserved. So we have this, so we have a conservation law, this distance, and we have a continuous symmetry, which is rotation. And the way that you see how those two things are linked is you can look at the form of the quadratic form or the metric. So I mean, the punchline of trigonometry is that x squared plus y squared equals z squared, the equation of a circle. Sorry, the Pythagorean theorem is okay. Pythagorean theorem a squared plus b squared is c squared is the same equation as that of a circle. X squared plus y squared is equal to r squared. So a circle takes the viewpoint of saying, oh, this is the locus of all points that satisfies this relationship. Well, Pythagorean theorem says, oh, if you have these 2 points, this third point is what's forced, right? It's just 2 different ways of saying the same thing. That's the connection between the Pythagorean theorem and this like rotational symmetry around circles. So the way to say this in trigonometry terms is, we are agreeing that we live on this circle. If we agree we live on this circle, that's like the conservation law in a sense. Then we also then we agree that given 2 legs of the triangle, we know what the whole triangle looks like. That's kind of a sucky way to say it. Okay, it'll be clear in a second, my analogy. So I'm gonna do a contour plot for the space-time interval. So motivated space-time interval with causal diamonds, and I'm gonna do a contour plot of x squared minus t squared, and we'll do x from -2 to 2 and t from -2 to 2, and contours we'll do, let's do like 20 contours. Nope. Hold on. I have to put it behind everything so you can actually see it. Great. So yeah, great. So here are the contours. So the contours of, okay, so here's another way of saying this. If I put the Euclidean norm over the whole space, you get an x squared plus t squared for every point. It's its distance from the origin. And then if that was the invariant law, then under Lorentz transformations, you should just travel along lines that preserve that value. So if the law was Euclidean distance is preserved, like that's the norm, that's the metric on the space that works, then when you hit it with a Lorentz transformation, you have to preserve that value. Okay, how do you preserve the Euclidean distance to a point from the origin? Well, you have to move along circles. Okay, if the conservation law was the Euclidean distance, then you have to move along circles. Okay, the conservation law is x squared minus t squared. So how do you preserve that? How do you preserve the conservation law of x squared minus t squared when you move under a Lorentz transformation? Well, you have to travel along. Where are my points? Oh, you can't see them. Damn it. Ah, you can't see my points. Why can't you see my points? What is it? Where are you? Okay, how do I show you the points? Hold on, I did this in another document. Let me just go grab that. Copy and paste. So we have hyperbolas. So what I did was this is just a graphics object. So I'll just copy this whole thing. Okay. Instead of using the contour plot, I wanted to use contour to prove a point, but that's okay. Great. Okay, there are our hyperbolas. So let's see what a point does. Great. So if the invariant quantity is x squared minus t squared, I made the points so huge because I thought they vanished. Okay. If the invariant quantity is x squared plus or x squared minus t squared, then when you transfer to another reference frame, you have to preserve that quantity. Okay. How do you preserve the quantity x squared minus t squared? Well, in the same way that the punchline of trigonometry is, triangles versus circles, and it's the same equation, the punchline here is that to preserve that quantity, you have to travel along the locus of points that preserves that quantity, which is by definition a hyperbola. And this is just like hyperbolic trigonometry, hyperbolic sine and hyperbolic cosine. Great. So we see that all of the points, time-like and space-like, travel along these hyperbolas. You can even consider the light points as traveling along hyperbolas. They're just the degenerate hyperbola, that is that x. But also the motion of these points would be like non-physical anyway, because like, what does it mean to talk about a point along a photon's journey? It's all the same for the photon. I even kind of like to think of the causality grid as one point. So this is the point I'll leave you with. Why do I like to think of the causality, or I like to think of this causality cone from the origin as one point in the space. Why? Let's do some topology. So I put a norm on this space. I put a metric on this space. It's not really a metric, it's a pseudometric. X squared minus t squared is a pseudometric. Why is it a pseudometric? Well, it's not positive definite. It's positive up here and it's negative. It's negative in the space-like regions. Or if you use t squared minus x squared, it's negative here and positive here, just depending on your choice. It's positive in one region, negative in the other. So it's not positive definite like you want a metric to be. It's also, but the real troublesome thing there about why it's not a metric is it's not non-degenerate. So the distance between 2 points that are connected by a light ray, let's think about that. What about this point and this point that are connected by a light ray, a causality line? You have a delta x, but you also have a delta t. And since we set the speed of light to 1, the delta x and delta t are the same. So you increased, so their space-time distance away from each other is delta x squared minus delta t squared, which is just delta x squared minus delta x squared, which is 0. The space-time interval between any 2 points that are connected by a causality line is 0. If you use the space-time interval as a pseudometric, if we use a pseudometric, so what is a pseudometric? If you use that pseudometric to mean far away, how far away they are now, they're 0 away. And this is the invariant quantity that matters in special relativity. So what we get is that objects that are separated by a causality line are 0 distance away in our pseudometric. If they're a positive distance away, then it's some physical distance inside of some physical relationship inside of our causality cone. If they're a negative distance away, it's some one of them is out here and elsewhere in this space-like region that you can't even measure because you need an impossible space-time ruler. But if it's 0, that means that they're connected by a causality ray. So then if you put a topology on the space where you say that points are identified by how far apart they are to other things, then all this entire X gets collapsed into 1 point because they're 0 away, right? So the topology on this space is weird. But that's consistent with the notion that a photon has no life or has no lifespan. Its entire universe exists at 1 point in space. So if you're a stationary observer, you have a non-zero space-time interval between you now and you now. That was like 1 second. So your delta x was 0, but your delta t was 1. So then 1 squared is 1, and you had a space-time interval of 1 between your those two instances of yourself. But the photon doesn't experience time. The distance from any 2 points that you choose on the photon's world line are 0 space-time interval away, which reflects how the photon experiences the world. So for this reason, this gives insight a little bit into the space-time interval is also what's called the proper time. If you want to calculate how many time steps, how many clicks of a clock have been measured for a certain observer, you measure the space-time interval from 1 point on their journey to another point on their journey. And we'll talk about that more next time. But if you want to know how time is being experienced for a person, you have to use this invariant quantity of the space-time interval. Okay, so a summary of the argument here. This is what really inspired me to do this seminar in the first place, is seeing this relationship right here. Here's another argument. This is how I originally wanted to motivate the entire seminar, but then I decided to build up the Lorentz transformation instead. I wanted to start top down. I wanted to say, okay, space isn't conserved, time isn't conserved. We need something that's conserved. If nothing's conserved, then we can't even talk about this. If everything's just up to reference frame, then or if everything's just changes in reference frame, we can't agree on anything. We have to be able to agree on something so we can do science. So what can we need to be able to agree on something. Turns out the thing we can agree on is the space-time interval. Okay, let's take that as given. So if we have to agree on the space-time interval, that means that when you change reference frames, the space-time interval has to be preserved for events. The events move based off your reference frame, but they have to have the same space-time interval. Well, what are the lines that you have to travel to preserve the space-time interval? Well, x squared minus t squared, that's the equation of a hyperbola. So any point along hyperbola has the same space-time interval. Therefore, when you do a boost from one reference frame to another, you have to travel along this hyperbola or hyperbolae. And then you can actually derive the Lorentz transformation from the spacetime interval, which I'm going to put in the notes. But so then you can derive the Lorentz transformation. So then you know how these points have to move. As you see here, these hyperbola totally constrain how the points move. So like if you know these hyperbola, then you already know what's going on about how these points move. I guess you could argue maybe they can move faster along one hyperbola than another, and there's some subtlety there in justifying why they move together. But anyway, okay, cool. And then right, and then going into an argument about quadratic forms. So you have a pseudometric, and then that pseudometric, you can interpret as a 2x2 matrix. And if you feed in two different points to both sides of the pseudometric, you get the distance between them, or the pseudo distance between them if you want. But another way of using a pseudometric, or it's a differential 2 form if you want, is as a quadratic form, which gives you not a norm in this case, but a pseudo norm. And that pseudo norm is again the spacetime interval. So I really liked this argument because I don't know if you guys like differential forms, but if you do, it's you have 0 dimensions, and you go up one size to like the tangent space and the cotangent space, and you go up another size to the second exterior product of the cotangent space and the second exterior product of the tangent space. But the thing is, we only live in a 2-dimensional space, so that space collapses back down to size to the 0 size by the Hodge dual. So anyway, there's like this Hodge dual between a 2 form and a scalar. So the 2 form is the pseudometric, and the scalar is the spacetime interval. So there's 2 ways of saying this. You could say the spacetime interval is preserved as a scalar quantity, or you could say you have a pseudometric, which is a 2 form on this space. And it's saying the same exact thing under this Hodge dual isomorphism, that having a pseudometric and having a conserved quantity are the same thing. Noether said that too. Having continuous symmetries, so symmetries along these hyperbolae, and having a conserved quantity are the same thing, or a conservation are the same thing. So that's really the this is the central pin of special relativity for mathematicians, is that space and time are fake, but this thing is conserved, the space-time interval, and the travels along hyperbola. Okay, end lesson. Any other questions before we sign off for today?
I think this is the shortest we've been yet.
Yeah, it is. Wow. Go us. Yeah. All right, great. Next time we'll talk about relativistic kinematics. So what does it even mean to have a velocity when space and time are fake? Because velocity of space is meters per second, but meters in second are fake, or meters in seconds are fake. And energy is kilograms meters per second squared, but meters in seconds, and even E equals mc squared says energy and mass are the same thing. So what's a kilogram? It's a huge mess. So we have to redo it. We have to start over. We'll start over. And then also, I think we'll have time next time to start talking about some paradoxes and how to resolve those. So weird, non-intuitive things with Newtonian thinking that happen, but that we have to think about differently with special relativity. Great.
All right, I'll stop the recording now.